Hello, this is Dr. Holcomb. In this video, we'll be talking about Fischer projections and Meso compounds. Fischer projections are structures that represent chiral carbons as the intersection of two lines. Horizontal lines are bonds pointing out of the page, while vertical lines point behind the page. Fischer projections are commonly used for carbohydrates, where the convention is to place the aldehyde or the ketone at the top of the structure. The conventions based on a perspective view aligned with the contiguous carbon chain as viewed from above. This places the substituents with wedges and the contiguous chain with hash marks. For Fischer projections, the wedges are omitted and the substituents are understood to be projected toward the viewer. This provides an efficient way to convey the absolute configuration of chiral carbons. With the horizontal groups always directed toward the viewer, we can easily reconstruct the tetrahedral carbon. We can assign the absolute configuration of the carbon by assigning priorities to each of the substituents. In this case, moving from the high priority to the lower priority groups gives us a tentative assignment of S. But the hydrogen, the low priority group, is on a horizontal line and is therefore facing toward the viewer. This reverses the stereochemistry and gives us an absolute stereochemistry of R. This assignment can be confirmed by redrawing the hash wedge structure to give a typical tetrahedral carbon center, which when viewed from below affords a Newman-like projection, which, using the same priority, gives us a R configuration of the chiral carbon center. Fischer projections are particularly useful for carbohydrates bearing multiple chiral carbon centers. The first step to producing the Fischer projection is to rotate bonds so as to orient the backbone such that it's receding from the viewer. Note this changes the orientation of the substituents on the carbon that's being rotated. Next, we orient our perspective view to place the backbone receding. When we follow the convention for carbohydrates and place the aldehyde on the top of the structure, the two hydroxyl groups are oriented on the right-hand side of the structure. Notice that only the chiral carbons bearing the hydroxyl groups are placed on the horizontal line. To assign the absolute configuration to the first chiral carbon, we begin with the priority of the substituents. Tracing the priority path gives us a tentative S assignment. But with the low priority hydrogen facing toward the viewer, the assignment's reversed and the carbon is assigned the absolute stereochemistry of R. Similarly, the second chiral carbon center is assigned an absolute configuration of R. The enantiomer of this compound is readily rendered as a mirror image. Pause and take a moment to assign the priority and absolute configuration to each of the carbons for the enantiomer. Using the same priority gives us the S configuration for each of the chiral carbons. As expected, the enantiomer of the RR isomer is SS. Care must be taken to convert a Fischer diagram to a zigzag diagram. We begin the process by rolling the molecule 90 degrees onto its left side. After a series of bond rotations, we achieve a zigzag structure. Reorienting the molecule gives us our zigzag structure with the substituents presented as hash marks and wedges. Pause the video now and take a moment to assign the stereochemistry to each of the three chiral carbon centers. The absolute configuration for this molecule is 2R, 3S, 4R. In general, for carbohydrates drawn according to the standard convention, carbons bearing a substituent on the right-hand side of the Fischer projection will be assigned R configurations, while carbons with substituents on the left-hand side will be assigned S configurations. However, it's always a good idea to confirm this with your own absolute configuration assignment. While it's possible to convert a Fischer projection into a zigzag structure using bond rotations, for more complex structures, it's a better approach to use the absolute configuration and reconstruct your zigzag structure accordingly. Begin the conversion by creating the zigzag carbon framework. Be sure that you have enough carbons. Next, draw the substituent and assign priorities, but don't connect the bonds just yet. This allows you to tentatively assign the carbon an absolute configuration. In this case, the configuration of the second carbon is R. This reversal of the assignment implies that the low priority hydrogen must be coming forward, placing the hydroxyl group receding back. The second hydroxyl also requires an inversion of the original tentative R configuration to give us the required S configuration. In this manner, each of the hydroxyl groups can be placed on the zigzag structure with the appropriate wedge or hash mark to give the correct absolute configuration for the chiral carbon center. Pause the video now and see how you do with converting Fischer structures to zigzag structures. Be sure to take the time to do these practice problems so that you're well versed in translating Fischer structures into zigzag structures. Here's a couple more problems if you feel you could use more practice. First, we assign the absolute configuration to the carbons of the Fischer projection. Then we create the carbon skeleton with the appropriate hydroxyl group substituents oriented in the proper wedge and hash marks to meet those absolute configuration requirements. Understanding how the absolute configuration assignment changes upon manipulating Fischer projections can add insight. For instance, rotating the structure by 180 degrees results in no change in the absolute configuration assignment. That's because such a rotation does not involve bond breaking or bond forming. Rotating by 90 degrees does, however, change the absolute configuration. This is because the low priority group is moved from a position in which it's oriented toward the viewer to a new position in which it's oriented away from the viewer. Such a rotation then produces the enantiomer. Swapping just two groups inverts the stereochemistry of the chiral carbon center and produces the enantiomer. If one group is held steady and the remaining three groups are rotated clockwise or counterclockwise, the chiral carbon center retains its stereochemical assignment. It's as if the molecule were being rotated about the axis of the group that's being held, and the base of the tetrahedron is simply moving in a clockwise or counterclockwise direction. Now it's time to pause the video for a moment and see if you can determine whether the following molecules are the same or are they enantiomers. Use the rules for manipulating Fischer projections, then confirm by assigning absolute configurations. Here are the relationships based on the Fischer projection manipulations. And here is the confirmation based on the assignment of absolute configuration. Before we move on to consider additional aspects of chiral carbon centers, let's take a moment to review the organization of isomers. Isomers may be constitutional, in which they share the molecular formula but a different connectivity. Or they may be stereoisomers, in which the atoms have a different orientation in three-dimensional space. Stereoisomers may be conformational or configurational. Conformational isomers differ by a rotation about sigma bonds. Configurational isomers may be geometric isomers or optical isomers. These two cis and trans alkenes are examples of geometric isomers. They are compounds that do not possess a chiral center. In contrast, optical isomers possess one or more chiral carbon centers. Optical isomers possess one or more chiral center. Molecules with one chiral center are chiral molecules and are optically active, that is, they rotate plane polarized light. Molecules with two or more chiral centers may possess a non-superimposable mirror image, in which case that mirror image is an enantiomer. Like molecules with one chiral center, enantiomers are non-superimposable mirror image pairs. Molecules with two or more chiral centers that are not non-superimposable mirror images are diastereomers. Diastereomers are chiral molecules. They are also optically active. Molecules with two or more chiral centers that have a plane of symmetry are called meso. Meso compounds are achiral and optically inactive. This dihydroxycarboxylic acid has two chiral centers. The number of possible stereoisomers for this compound is given by 2 raised to the nth power, where n is the number of chiral centers, and in this case there are 4 stereoisomers for this compound. The 4 stereoisomers consist of 2 enantiomeric pairs and 4 diastereomeric pairs. The relationship between the enantiomers can be seen by the reflection of RR to give SS and RS to give SR. The diastereomers, which are not non-superimposable mirror images, do not cancel. So the relationship between RR and RS is not a mirror image. Similarly, SS does not reflect to become SR. Compounds with 2 or more chiral centers which possess a plane of symmetry are achiral. Molecules with a plane of symmetry do not have non-superimposable mirror images. In the case of this cis 1,2-dimethylcyclobutane, rotation about the central axis of the mirror image provides a superimposable molecule. The compound is therefore achiral and optically inactive. In essence, the R configuration of one chiral carbon counteracts the S configuration of the other chiral carbon, in which they both possess the same substituents. So the optical rotation afforded by one chiral carbon center counteracts the optical rotation afforded by the other chiral carbon. To determine if a molecule is meso, we can apply the meso test. First we ask, does the molecule have chiral centers? If the answer is no, it's not a meso compound and it's achiral. If the answer is yes, we ask another question, does the molecule have a plane of symmetry? If the answer to that question is no, the compound is not meso, it is a chiral compound and it's optically active. If the molecule does possess a plane of symmetry, it is a meso compound and it's achiral and optically inactive. Let's apply the meso test to the following molecules. In the case of the diol, there are no chiral centers, so the compound is not meso, it is achiral and not optically active. Our second compound, a carbohydrate, has 2 chiral centers. And notice carefully, there is no plane of symmetry. The molecule is chiral and optically active. Our third example also has 2 chiral centers. And both chiral centers have the same set of substituents. One center has the absolute configuration S, the other R. These 2 chiral carbon centers cancel each other out, and in fact there is a plane of symmetry. With 2 chiral centers, a plane of symmetry, the compound is meso. It is therefore achiral and optically inactive. Our fourth compound also has 2 chiral carbon centers. However, this compound has no plane of symmetry. The absolute configuration, S, does not translate into R for the other chiral center. The molecule is SS and is therefore chiral. So this molecule with 2 chiral centers has no plane of symmetry, is chiral, and is therefore optically active. Now it's your turn. For the following 3 compounds, determine whether the compound is chiral, meso, and optically active. Pause the video and work it out for yourself. Our first molecule has no chiral centers. It's achiral, not meso, and not optically active. Our second molecule has 2 chiral centers, which are assigned an RR configuration. That R does not reflect to be S indicates that there is no plane of symmetry. The molecule is therefore chiral, it's not meso, and it is optically active. The third molecule is also chiral, as it has 2 chiral centers which do not cancel each other out. This compound is then also chiral, not meso, and optically active. In some cases, your analysis may require an initial operation or that you redraw the molecule. Pause the video now and take a moment to consider how you will proceed with the analysis for these 2 compounds. In the first case, assignment of absolute configuration for carbons bearing the same substituent reveals that there must be a plane of symmetry. This is because S reflects onto R. This is confirmed by rotating about the sigma bond and redrawing the sawhorse structure. Given the presence of the 2 chiral centers, the compound is meso, achiral, and optically inactive. In the case of the 1,3-dimethylcyclohexane, there are clearly 2 chiral carbon centers. Redrawing the structure reveals that there is a plane of symmetry. This compound is therefore meso, achiral, and optically inactive. This is confirmed by analyzing the absolute configuration of the chiral carbon centers, each of which has the same set of substituents. R cancels S. Furthermore, both substituents are equatorial, so R equatorial does indeed cancel S equatorial. What could we conclude about the 1,2-dimethyl trans-cyclohexane? Is a solution of this compound optically active? Pause the video and conduct your own analysis. The first step is to redraw the cyclohexane with the 1,2-dimethyl substituents. The absolute configuration, R and S, suggests a mirror plane exists. However, we can see with a deeper analysis that R equatorial does not reflect onto S axial. Therefore, there is no plane of symmetry, and this molecule is chiral. In solution, this molecule undergoes a ring flip. While the assignments remain the same, the equatorial substituent becomes axial, and the axial substituent becomes equatorial. Reorienting B and comparing it with conformer A reveals that the 2 conformers are non-superimposable mirror images. This is confirmed when we combine our absolute configurations with our axial and equatorial assignments. For conformer A, we have 1R equatorial, 2S axial. For conformer B, the 2 methyl groups are S equatorial and R axial. When the axial and equatorial positions are taken into account, R cancels S. A solution of the compound is therefore racemic and optically inactive. I hope this video has been helpful. Be sure to let me know in the comments below.